Hello, Algebra 1 students, and welcome to your newest topic of study, Topic 9, called Factorable Quadratics. Now, we just came out of a unit, Topic 8, where the first half was about how to add, subtract, and multiply polynomials, and then the second half, the big part, that box method, was all about factoring polynomials. So that factorable quadratic statement means we are able to put a quadratic, something with x squared, right, the standard form right here, we're able to put that into factored form. And so this unit is going to be, why is that important? Why did we spend so much time learning how to put something into factored form? What can we do with it? And the first half of the unit, starting with today, revolves around goal 24, which is, again, essential. And our end achievement by this goal, by the end of these next couple lessons, is to solve a factorable quadratic in the form of ax squared plus bx plus c equals 0. Because maybe you noticed, and if you didn't notice, you'll know now, we didn't actually solve a single equation all of last unit. There wasn't even an equal sign all of last unit. So now we're going to move back into the idea of solving for x, and our daily goal for today is to solve a polynomial in factored form using the zero product property. And we don't know what the zero product property is, but hopefully we'll learn that by the end of the day. So let's get to an opener. Let's get some review. Setting an equation equal to 0 and then solving finds the zeros, or you can call them the solutions for that equation. So let's go ahead using SADMAP. That's what we've always used so far to isolate x. And let's isolate x in each of these three equations. Ready, set, go. All right, well, our first equation shouldn't be too bad. And really, don't forget what we're trying to do here, because you could honestly probably find the answer for 2x equals 0 just by remembering at its core, this means 2 times what number gives you 0. And hopefully you're thinking, I'm pretty sure the answer is 0, because if you replace x with 0, 2 times 0 is 0. 0 equals 0. But how could we algebraically prove that to ourselves? Well, we take a look at the number attached to x. That's 2. It's attached by multiplication, so we need to divide that 2 right back off. And that gives us just x equals 0 divided by anything is 0. If we look at our next one, we have a 2 that's attached by multiplication and a 6 that's attached by addition. So SADMAP, of course, works from the top to the bottom. So we start with addition and subtraction. We undo addition with subtraction, so we subtract that 6 from each side. That leaves me with 2 times x equals negative 6. Took care of the addition. Now we have to undo the multiplication. Just like before, we divide by 2, and we end up with negative 3. Pretty easy to check as well, I think. We just take our equation, and instead of x, we replace or substitute the x with negative 3. And once we are checking or evaluating this side, then we use PEMDAS. So 2 times negative 3 is negative 6, and negative 6 plus 6 is 0. Last but not least, x squared plus 6x. We might have a bit of an issue with this problem. Now, again, using some logic here, you should be able to come up with at least an answer or two that works, but we definitely need to understand why there's an issue. We always follow SADMAP to undo what's attached to a single x. But the problem on C here is that we have 2 different x's. This first x has a square happening to it, and the second x has multiplication. And unfortunately, you are not going to be able to undo the square or the multiplying by 6 from both of them to be able to combine these together. And I'll give you 2 examples of why. Let's say that you looked at that square first, and you said, ooh, a square. I know how to undo a square. We have to square root. And you're right. But whenever you do something to undo a value attached to x, you have to do it to the entire side. So I could add in this square root here. Now, the square root of 0, and I'll just work this over here, is 0. But the square root of x squared plus 6 is really tough because there's that addition in between. And we know that we're not allowed to distribute a square root, which would kill puppies. And even if you could distribute a square root over here, square root of x squared plus the square root of 6x, this could become x, but then this 6x is stuck inside the square root, and we still can't put these x's together. So we're only able to solve for x if we can simplify that down to one instance of x. So if that doesn't work, you might want to try the other option, which hopefully you're thinking about, which is, oh, this 6 is attached by multiplication. Let's undo that by dividing. But just like anything else, if you multiply or divide, you have to do it to both sides. And so what ends up happening here is 0 divided by anything is 0. 6x divided by 6, well, we have to distribute that 6 whenever you multiply or divide. So it looks like this. This would give us x, which is equal to 0, but then this is x squared divided by 6, and now we've kind of just gone in circles, and we still have a 6, but now it's attached to the x squared, or the x, and so is the square, and we still have this x over here, and these still aren't like terms. So again, you're not going to come up with something that really seems to work here, which is a bummer, but that also leads us into the main point of today. Most problems that we're going to do this unit are going to focus on how to solve equations in standard form, ax squared plus bx plus c, and sometimes in factored form, x minus p times x minus q. And both of those have multiple x terms. Can we see the x squared and the x? This one has an x here and an x there. And so we're actually going to stray away from SADMET for a little bit. We'll come back to it later on. And we're going to see if we can discover how we can actually solve equations like this. So I have 3 questions for you. Question 1. If you're given a times b equals 0, where a and b are just standing in for 2 random numbers, then what do you know about the value of a, or maybe the value of b? And another way to phrase that is they're basically saying one number times another equals 0. Okay? And what if I said, I know that a is 4? What does b have to be? Or maybe I told you that b is negative 6. What does a have to be? Or maybe I don't know either of these. What does one of them have to be? And hopefully you're saying here, oh wait, I know that one letter must be equal to what? And that's right, 0. The only way we know in math so far to multiply to equal 0 is if one of these 2 values here is 0. There's no other way, right? If you think of the number 2, 2 times what is 0 if that number is not 0? Well, there is nothing that we know of. So 2 times 0 is 0. Okay, well, let's ask the same question again, but now with 4 variables. A times b times c times d equals 0. What do we know about one of those? Well, and hopefully you can say at least one, I'll just say unknown, must be 0. In fact, all of them could be 0. That would be true. Or 3 of them could be 0, right? 3 times 0 times 0 times 0 is 0. But there's no way to make 0 unless at least one of those is 0. So we get the idea, right? If you multiply to equal 0, one factor has to be equal to 0. Well, let's ask that same question again, but let's stray away from 0. Judy and Carrie are having an argument. Judy thinks if she has the equation a times b equals 5, and I'll write that over here, a times b equals 5, then she has found 2 and only 2 solutions. Either a is 1 and b is 5, or, right, a is 5 and b is 1. She's like, I found them. That's it. However, Carrie argues that she actually found 4 other sets of values, and I'll write them out here for you. Here's 1, 2, 3, and 4. Carrie said she found 4 other combinations that also multiply to equal 5. Can you guys find those? Can you find more than those? Take a minute, pause the video, see what you can do. Ready, set, go. All right. Well, at this point, hopefully you did come up with something, and my students are very clever about this. I'll give you a couple options. Some students instantly will say, oh yeah, -1 and -5, and they're 100% right. -1 times -5 is 5. And then they go, well, we could switch those, -5, -1, and I challenge them and say, you can, but could you find a different way? And then others will say, oh, I thought of money, and I know if I have $2.50 and double it, I get 5. And you're right. You could, of course, do the negative version of that, but can you do others? What about 10 times 0.5, or you can even think of it as 10 times 1/2. I'm pretty sure half of 10 is 5, right? Or you can even go further and say 25 times 1/5 is 5. Right? We spent all last unit factoring, but we only factored with nice numbers. There could be positives, could be negatives, but we can't forget that there could also be decimals here too. Now, re-asking the question, if we know a times b equals 5, what do we know about a or b? Does one of them have to be 1 or one have to be 5? And no, I don't think so. Look at all these counter arguments we have over here. There are many different ways to make 5 where we don't know anything about either of the factors. And so, with all of this together, we can go through and state the zero product property. To solve a quadratic equation containing multiple terms with x, just like the ones we saw up above, we use what is known as the zero product property. Breaking that down, we need to have something to do with 0, something to do with a product, which of course means multiply, and a property, well, a property just means something that's true. So, in order to use the zero product property, you have to have an equation in factored form. And as a reminder, factored form is when we have these multiple factors here. Okay? And those multiple factors can be more than 2. 2, 3, 4, 100, doesn't matter. And this is very important, that factored form better be equal to 0. Because now this is like a times b equals 0. And what we learned up above is that either, or maybe both, one of those factors must be equal to 0. So what we're going to do is we're going to take one of those factors and set it equal to 0, because either that whole factor will be 0 or the other factor will equal 0. Once we do that, because each of these factors are going to have x in them, now we have two smaller equations, but we've managed to split the x's up. Now there's only going to be one appearance or one instance of x in each mini equation. And so we can get back to SADMAP and actually solve those equations. Now it's a little bit tough to hear those without examples, so let's do some with some actual numbers here. Solve each equation below by finding all solutions. If you finish early, check your solutions, yes, each of them, using the check column on the right. Now, in the interest of time here, I'm going to solve the first one and check the first one. I'm going to skip the rest of the checks, and I'm just going to solve the rest of the problems down below. But if you have more time, you're waiting for your class, you want to really expand your comprehension, you should try the other checks. So let's try this first problem. I have a factor x minus 3 times a second factor x plus 2, and it's equal to 0. Well, if that's the case, then I'm going to take my first factor, x minus 3, and set that equal to 0. Then I'm going to take my second factor, x plus 2, and set that equal to 0. Because I know when multiple factors multiply to equal 0, then one of those factors has to be 0. The only way we can do something times something to equal 0 is if one of them is 0. So let's see what makes each of them 0. There are parentheses here, but you'll notice I didn't even write the parentheses on the green one. I'll add those in for now, but I'm going to take them right away again because there's nothing outside the parentheses, nothing to distribute, so we can just drop our parentheses. Once we're here, it's just a matter of isolating x, and so now we're back to SADMAP because each one of my small equations only has a single x. So for my first one, I'm going to go ahead, add 3 to each side, right? Undoing the minus 3 leaves us with x equals 3. Our second one, we're going to subtract 2. And this leaves us with x equals negative 2. And we found our two answers. It's pretty easy to solve. Honestly, these smaller equations are generally easier to solve than ones that we've done in the past. And that's usually because our factors are pretty basic factors. So you should be excited. You're like, ooh, I can solve these. This isn't bad at all. Let's check this, though. Let's make sure we did it right. So I have two solutions to check. X equals 3, x equals negative 2. And we check the solutions in the same way every time, right? We take the problem, which over here was x minus 3 times x plus 2, and that's equal to 0. And I'm going to do it one more time down here. X minus 3 times x plus 2 equals 0. And notice that I'm actually replacing both of the x's with my answer, right? We split it into a smaller equation, but this answer has to work for everything up above. So let's see if it does. It is 3 minus 0 times 3 plus 2. Now to simplify this left side, we're back to PEMDAS. 3 minus 3 is 0. 3 plus 2 is 5. These are attached with parentheses or with multiplication. And 0 times anything, 0 times 5 is 0. Do we see how our answer turned one set of parentheses to 0? So what do you think will happen with the other one? Negative 2 minus 3, negative 2 plus 2. We get negative 5 for the first and 0 for the second. That looks good so far. Negative 5 times 0 is 0, and 0 does equal 0. So both my solutions are correct. Now, if you see a problem like this on a quiz and they ask you to find all solutions, you do need to list all of your solutions. And I had two here, x equals 3 and x equals negative 2. All right, with that being said, why don't you guys try these other four? They're not too bad. And then we will come back together and see how you did. Ready, set, go. Well, on this second one, we'll just do the same thing. I'm not even going to bother to write the parentheses here, right? And hopefully we're getting to the point when solving equations where we can do some mental math here, right? To undo the subtracting 3, we add 3 to both sides, which brings us to positive 3. Then, to undo multiplying by 2, we divide by 2. Now, 2 doesn't go nicely into 3, so we can actually keep this as the fraction, right? We do this a lot in Algebra 1. You can keep it as the fraction 3 divided by 2. Or if you're comfortable with this and you say, I know 3 divided by 2 is 1.5, that's totally fine. Let's try the other. Subtract 2 from each side, divide by 3, keep it as a fraction. Doesn't seem very nice. You can write this as a decimal. However, please go out at least 3 decimal places or put the exact decimal by not saying 0.6. 2 over 3 is not 0.6. It's 0.6 repeating, right? And you're like, that's the same thing. Well, 0.6 repeating is 0.66666 forever. 0.6 is 0.60000. And that's really the difference between 60 cents and 66 cents, which you're like, well, that's not that big of a deal. You're right, but it is different. So if you have the ability to state something true, you should state it. All right, our third one. Let's go ahead and solve each of these, but we have something interesting happening. We have this 2 out front. Now, what's happening inside is we have 2 times this guy times this times this. And we don't actually distribute 2 to every set of parentheses. You can choose which set to distribute it to, but it doesn't really matter. You only can pick one set, though. So let's say that you're like, okay, I want to distribute the 2. So you get 2x, 2 times 0 is 0, minus 0. Then this stays negative x plus 1. I'll put the invisible 1 here. And 3 plus 6x equals 0. That's totally fine. And then you can go through and set each of these equal to 0. 2x minus 0 equals 0. Negative 1x plus 1 equals 0. And 3 plus 6x equals 0. I think the minus 0 is kind of irrelevant here, right? So really we just have to divide by 2, and 0 divided by 2 is 0. We can subtract our 1 from both sides and divide by negative 1. Negative 1 divided by negative 1 is 1. Last but not least, notice this is 3 plus 6 times x. 3 is adding to x, and 6 is multiplying. Through SADMAP, we know we undo the adding 3 first, so I'm going to subtract 3 from each side here, and that will leave us with 6x equals negative 3. Finishing this off, we divide by 6 to get negative 3 over 6, or if you reduce that fraction, negative 1/2. Now, one important note. I distributed the 2 inside, but some of you might ask why, and that would be a good question, because we could always group 2 in parentheses. If you group the 2 in parentheses, that actually leaves us with 2 separate factors, the factor 2 and the factor x minus 0. So what would happen if we set those independently equal to 0? 2 equals 0, and also x minus 0 equals 0. Well, x minus 0 equals 0 is pretty easy. Add 0 or just drop it, we get 0, which not coincidentally is the same answer we got up above. Because up above, we distributed the 2, which means we multiplied everything by 2, but then at the end, we divided the 2 back out. So really kind of that canceled our distributive property. But then the second question you should ask is, what about this 2 equals 0? What's the answer there? But this is so last semester. We saw that when a number is not equal to another number, but there's an equal sign in between, that's a false statement. And anytime we have no variables and we get a false statement, that means that there is no solution for that small equation. It's not no solution for everything. It's just no solution for this first part. And so what usually ends up happening is if you have a number out front, most people don't do anything with it. You can actually just forget it's there, because it's always going to be a no solution situation. The nice part, though, is if you forget that and you distribute, you'll still get the right answer. All right, let's move a little quicker. 3x times 6 plus 3x equals 0. Think about those parentheses. Your factors to have an answer always have to have x in them. So I have one factor here with x, but there's another x over here. And you could group this as 3x, that's fine. Or you could group it as 3 and x separately. You could see it as 3 factors or 2. And I'm actually going to do this one because 3 equal to 0 doesn't have a solution. X equals 0 is already solved, which is pretty nice. And 6 plus 3x equals 0 does actually need some solving. But that's good because otherwise our brains would get kind of bored here. So I'm going to subtract 6 from each side. 3x equals negative 6. And then I'll go through and divide by that 3. Negative 6 divided by 3, I believe, is negative 2. So there are 2 answers here. And last but not least, problem 5. Problem 5 is a little different because we're equal to 2, but I think it would make sense that we could just use our same strategy. We could take this 2x minus 4 and set that equal to 2. And then we could also take this x plus 3 and set that equal to 2. So we add 4 to each side. 2x equals 6. 2 times what is 6? 2 times 3 is 6. Over here, subtract 3 from both sides, and I'll show the step. Negatives can be tricky. 2 minus 3 will get us negative 1. Now, I mentioned I'm not going to check all of them. It's a bit of a white lie. I'm going to check this fifth one. And the reason I want to check the fifth one is because the equation equaled 2 instead of 0. And so that suggests that there might be a weird issue going on since that was different than all the others. So to check it, let's just check one of them. I'll just check the 3 over here. So I'll go ahead and check x equals 3. And my equation was 2 times whatever x was minus 4 times whatever x was plus 3 had to equal 2. And the x that I'm checking here is 3. Okay. So let's start simplifying what's inside the parentheses. We know 2 times 3 is 6, and 6 minus 4 gets us positive 2. 3 plus 3 is 6, and 2 times 6 is 12. Uh-oh. Do we see the issue? Yeah, 12 is definitely not equal to 2, which means x equals 3 is not a solution. And yeah, we do need to remember back to our definition of the zero product property, and that's on that previous page, right? Our zero product property says you have an equation in factored form, which we did, but also set equal to 0, which we didn't. And that, again, directly relates back to Judy and Carrie's argument, where they said they had two numbers multiplying to equal 5, so they knew something about one of those numbers. But did one of these have to equal 5? No, it did not, right? Look at all these different options where they didn't equal 5. And so on this fifth problem down below, when we're equal to 2, we are not allowed to do this. I'm just going to write a note and say not equal to 0. And at this point for today, I'm just going to say we don't know how to solve these yet. Eventually we'll learn them, but not today. And so we're just going to leave it there. If it's equal to a different number that's not 0, we don't know the solution yet, you can skip it for now. Okay, well, let's go ahead then and remember one more thing about the opener. It would be lovely if all equations were already in factored form, but sadly that's not the case, right? If you think about the third problem from the opener, the third problem from the opener was not in factored form, and this isn't quite the third problem, but it's pretty similar. You have an x squared term and an x. Not factored form because I don't see those parentheses multiplying together where each of them has an x. Okay, so what if we wanted to try and solve this using SADMAP? We already talked about how undoing the square and the 6 wouldn't be great, but let's do some not good math. It's okay math, and we don't do too much wrong. We actually only really do one thing wrong, but it's important to go through and look and understand what's wrong with this, and we'll understand that by the end of the page. So, first thing I'm going to do, I'm going to add 6x to each side. And it should make sense because there's this x which has a square that's an exponent, a 3 that's multiplying, and a 6x that is subtracting. So I'm just thinking through SADMAP here. And I undid my subtracting 6x by adding it. All right, this leaves me with 3 times x, which has a second power, equals 6x. Next up, I'm going to undo the multiplication on both sides by dividing by 3. That leaves me with x squared equals 6x divided by 3 is just 2x. Okay, so we got rid of that and that. And the last thing that is left is an exponent. Now we already saw that undoing an exponent with a square root wasn't great because it traps this x inside the square root and doesn't help us get x alone. But don't forget the definition of x squared is that x squared is actually x times x. And whenever you have something multiplying, can't you undo it with division? Couldn't I divide both sides by x here? And that leaves me with x equals 2. Okay? And in fact, if you check x equals 2, 3 times 2 squared minus 6 times 2 equals 0. I'm going to check that 2 right here. We're going to follow PEMDAS, which says do the exponent first. That's 4. Then we do the multiplication. 12 minus 12. 12 minus 12 does equal 0. 0 equals 0. So it seems like that PEMDAS, or SADMAP in this case, actually got us the right answer. And it kind of did. But if you were on a test and you listed this answer, you actually wouldn't get full credit. So let's talk about why you wouldn't get full credit, what the bad math was over here, and then we can go through and learn how to solve this problem. So we're going to start by introducing a very important theorem in algebra. Arguably, it's the most important theorem in algebra. We are going to explore the Okay, so to get a better handle on what's wrong with this problem, it's a great time to be introduced to a very important theorem in algebra, arguably the most important theorem in algebra. We're going to explore the fundamental theorem of algebra. Now, having taught this a few times in the past, I realize that out of the 4 words here, fundamental theorem of algebra, my students are very familiar with the word of and a little less familiar with the other 3. So what I'd like you to do is to take a minute and quickly define these 3 words. Use your phones, use the internet, use your friends, whatever sounds good. Your definition should be 1 sentence or even shorter than a sentence. And yeah, that shouldn't be too terrible. Then we'll try to put all of it together. Ready, set, go. All right. So fundamental-wise, fundamental, a lot of my students looked it up and said it was like core or it was a basic principle, right? And you hear that a lot in, let's say, sports. If you practice your fundamentals, basketball fundamental might be dribbling, right? You're going to dribble before you learn how to play a 2-3 zone defense, right? That's not a fundamental, dribbling is. So the fundamental theorem of algebra, this is like the core theorem of algebra. Now, what's a theorem? A theorem is a rule, or it's something that's understood to be true. So it's like a true statement, right? A lot of times in science, you'll put together a hypothesis, a thought, is this going to be true? And then you'll prove your hypothesis and say, okay, this is a theorem. I am convinced this is true. So this is a core rule of algebra. And what is algebra? Well, at its basic, algebra are basically the tools you use to solve equations. And so I'm actually going to simplify it a little bit further, and it's not quite accurate, but I think it works for this situation. It's really using SADMAP to solve equations. It's the idea that if you do something to one side, you have to do it to the other. Okay? So the fundamental theorem of algebra is basically a core rule of how to solve equations. And you might be sitting there thinking, well, wait, how come we haven't heard of this before? We've been solving equations for 3 or 4 years at this point. If this is such an important rule, why are you just telling us now? Well, the reason is it hasn't been relevant to you in the past. So let's discuss the fundamental theorem. It gives us an important piece of information about polynomials. Remember, our polynomials are like ax cubed plus bx squared plus cx plus d, right? You can have any exponents you want, and we worked with those at the beginning of topic 8. Now, you didn't know about polynomials before Algebra 1. And so before Algebra 1, you just had x to the first power equations. We'd call that a first degree polynomial. Because remember, the largest exponent in a polynomial is known as the degree of the polynomial. The one that I wrote up here has a degree of 3. It turns out, though, that that degree is actually super important because the fundamental theorem of algebra tells us that if you set a polynomial equal to 0, then the number of solutions, so the number of x values you find when you isolate x, is equal to the degree of the polynomial. So let's look at a few examples below. Use the degree to determine how many solutions there are. We're not actually solving the polynomial, though. So our first equation is set equal to 0. Check. Good so far. And then we need to examine the degree. So we look at the first one and say, what's the largest exponent? The largest exponent is 2. So this is a polynomial of degree 2, and that means when you solve for x, there will be 2 solutions. So on and so forth. 3 solutions, 2 solutions, 2 solutions. But then we get to 5. And 5 can be a little bit tricky because you might look at it and say, oh, this is x to the first power, so there's only going to be 1 solution. But didn't you guys just solve problems like this with 2 sets of parentheses on the previous page, right? You went through and you said, oh, there's 2 sets of parentheses. Well, let's get a good example, this guy up here. How many solutions were there? There were 2 solutions. So then you might think to yourself, well, does this break the fundamental theorem of algebra? And the answer is no, because this equation doesn't have a largest degree of 1. It isn't just x to the first. Remember, if you were to use a box over here, and you don't have to write the box, you can just take a look, and you did 4x minus 3 and 2x plus 1, and you multiplied it out to put it into a different form, equivalent, the same, but different looking, you get 8x squared. 4x, negative 6x, negative 3. And so we can see that the degree here is 2. There are 2 solutions. One of my other students said, oh, is it like the number of pairs of parentheses you have? And the answer is yeah, as long as each one has x to the first power, yeah. And so on 6, if you look at this guy, you might look at it and go, ooh, x times x, that's x squared. But don't forget about the third x. X times x is x squared, times another x is actually x cubed. So this equation, if you use some boxes to multiply it out, would be x cubed plus a bunch more items equals 0. And so there are 3 solutions for the last. Now, what about the problem at the top of the page? If you compare that to problem 4, I think you'll notice that they're the same problem. And that means, based on problem 4, that there should be how many solutions? Well, that's 2. So how do we find both solutions to that equation? Well, since today's lesson is on the zero product property, we should probably make sure the equation set equal to 0, which it is, and that the equation is in factored form. But I don't think problem 4 is in factored form. Factored form would have those parentheses with x to the first power. So is that an issue? Well, it might be, unless you were not a student who just finished off topic 8, which was all about factoring polynomials. Do you remember how to put this into factored form? There's 2 different ways, and kind of the longer way, but the way that seems to make more sense to my students, is you actually make a box, and this box is only going to have 2 parts. And that's because if you look at these, if you can ever find something in common to every term, and there's only 2 terms here, and that thing that's in common has to do with a variable, you really only need a super basic box. 3x squared is 3 times x, and negative 6x is negative 6 times x. Okay. From here, we just need to find what they have in common. And so we'd say, oh, they each have an x in common. And that leaves me with a 3x and a minus 6. So the factored form for this equation is actually, and I think I'm just going to do this straight down below here, is the x that I pulled off to one side, and then the top of the box, 3x minus 6, equals 0. And hopefully you can see if you distribute here, we get back to where we started, which we should, because we haven't changed the value of the equation, just the look. Now we're in factored form. So let's make 2 equations. X equals 0, 3x minus 6 equals 0. Now, you might have realized that when I went through and did this problem, we could have factored this in a different way. And in fact, I'm going to show you this a second way right here. And this might fall more in line with how we've factored in the past. And I draw a box every time. You totally don't need to do a box, right? You could have just said, oh, I see that there's an x in common, so this just becomes x times 3x minus 6 equals 0. great, and then gone from there. Perfect. The box is a nice way for those visual learners or someone that wants to see kind of those steps inside the steps. So let's look at this a second way, though. Same idea as before. Go through, draw the exact same box, 3 times x, and negative 6 times x. I'm going to start with the same thing. I'm going to say, okay, they each have an x in common. We're going to factor out that x. However, we also should realize that when we learned our greatest common factors last unit, that there is something that 3 and 6 have in common. If you have your factor sheet around, you'll see that 3 has factors of 1 times 3, and 6 has 2 sets of factors, 1 times 6, as well as 2 times 3. And so they actually both have a greatest common factor of 3. So I'm going to go ahead and divide 3 out of both of those. 3 divided by 3 is 1. Negative 6 divided by 3 is negative 2. And then, of course, we can still leave our x that was here, no x over here. And so we actually factored this one into 3x on one side and 1x, I'll drop the 1 though, minus 2 still equals 0. So you might be looking at this saying, well, wait, these look like different factored forms. Will we get the same answers? And let's see. Well, if we take the 3x and set that equal to 0, x minus 2 equal to 0. Okay. Well, we can go through and we can double check. Okay. So now notice on this right side, I'm actually going to go through and finish solving here. I'm going to add my 6 to both sides. That leaves me with 3x equals 6. And then divide both sides by 3, which leaves us with x equals 2. So 2 answers, 0 and 2. On the left side, we could divide off the 3. And remember we mentioned earlier that you don't actually need to bring the 3 with you. You could set 3 on its own. You could just ignore the 3 when you have that multiplication. You're going to end up dividing it back out anyways, but you can bring it. Gives us x equals 0. And I bet over here you can see we add 2 to each side and end up with x equals 2. Same answers? Same answers. So, what should we factor? Well, it's ultimately up to you. When you're factoring, though, each set of parentheses in your factored form needs to have an x. So at a bare minimum, you need to be taking an x out of each part of the inside of the box. So I'd say that this side is the bare minimum factored form. If someone asked you to put something into factored form with the greatest common factor taken out, then they mean this. 3x is the largest you could take out of both of those terms. Either way, though, both will work. Whatever appeals to you. If you're still struggling on that greatest common factor with the 3, then just take the x out and it'll work each time. Alrighty. So now we understand this fundamental theorem of algebra. Right? Our first attempt over here, we only got one answer. We were pretty satisfied with ourselves. It worked. However, the fundamental theorem of algebra told us that because there was a square in the problem, we should have had 2 answers. What were the 2 answers? Well, here's how we do it. We can't use SADMAP if you have 2 different types of x's, x squared and x. We can't use SADMAP. That's for isolating a single x in an equation. More than one x, if they're not like terms, factoring is our only other method we've learned at this point. Once you've put this into factored form, that allows us to make 2 equations that only have a single x, and now you can use SADMAP. So to finish off today, we have a couple practice problems on this last page, as well as some bonus problems at the bottom. You guys should give those a shot. These first 6 are all about those factored form problems like the previous page, that fundamental theorem of algebra. And then we have some bonus review problems at the end. So good luck. Once you're done or once you've reached a stopping point, unpause, skip to the part you need help on, and we'll go from there. Ready, set, go. All right, we're back. Solve each equation below, listing all solutions. Don't forget, you need to make sure your equation equals 0, and you'll probably have to put it in factored form. So if we look at our first one, a squared and 5a. Well, we have 2 different types of a's, so we're going to have to use that factored form. Now again, you can use a box. For most of these, though, I'm not going to use a box just because it's a little bit slower to write it each time, but the first time we can at least demonstrate. They have an a in common. Then we have an a and a 5. And so if we look at this, We have an a that I took out to the left with an a plus 5 left inside equal to 0. Could you see that without using the box, right? They each have an a, so we took an a out front. Once we're here, two equations. A equals 0. A plus 5 equals 0. A equals 0 is nice. That one's already done. A plus 5 equals 0 needs a little bit of that magic algebra, some math magic here. But we end up with A equals -5, and we should be set. All right, problem 2. 3x squared minus 9x. Okay. You could realize that they each have a 3 in common and they each have an x. I'm just going to be lazy and only factor out an x from each of these. So if I just take an x from 3x squared, now it's just 3x. And you can check x times 3x is 3x squared. If I take an x away from 9x, it's just the -9. Now I have two sets of parentheses. X equals 0, or 3x minus 9 equals 0. One is already solved. Let's finish the other. Adding 9 to each side leaves us with 3x equals 9. And you don't even need to finish off SADMAP here. 3 times what is 9? Well, 3 times 3 is 9. X is 3. You could divide both sides, but hopefully that's easy enough to see. But then we come to our third problem. And our third problem has a bit of an issue that we haven't encountered before. And in fact, sneaking up above is the answer. It tells us that we need to make sure our equation equals 0. And on the third problem, our equation does not equal 0. Luckily, though, we've just spent about 8 months working with algebra, and so we should know how to manipulate an equation, move terms around in an equation to get a 0. In particular, if you look at this right side, this is a positive 2x. And now people might say, oh, well, you would divide both sides by 2. You can divide by 2, but that's still going to keep an x on that side. If we need one side to be 0, and it doesn't matter which side, I usually prefer the side with the smaller term, we need to add or subtract. That's really the only way we make zeros in math. So I'm going to go ahead and subtract a 2x from each side. Now, it's important to keep your equal sign. Make sure those stay lined up. Anything minus itself is 0, but because that was the last thing on the right side of the equals, we better keep the 0. On the left side, don't make the common mistake and try and put those together. They are not like terms, x squared and x. They just stay right next to each other, 4x squared and -2x. And then from here, you could take 2x out of each. You could just take an x. I'll do the greatest common factor, though. This time, I'll take a 2x out of each of those terms. 2 times 2 gets you 4. X times x gets you x squared, minus 2x times what gets you 2x? Well, that's got to be a 1. Again, if that's a little bit too much, just take the x. If you just take the x, it would be x times 4x minus 2. And you're still going to get the same answer. So from here, two equations. Notice on this 2x, we don't need to bring the 2 along with us. The 2 is just that constant we've discussed before. I'm just going to bring the x. And then the other is 2x minus 1 equals 0. Let's finish solving. I'm going to need to use a little bit of the rest of this column to help me out. 2x equals 1. And last but not least, divide by 2. And we end up with x equals 1/2. Or 0.5 if you would like. All right, 3 to go. 6n squared equals 15n. Well, let's subtract that 15n from each side. Same as we did before, right? We get the idea now. We want to make a 0 here. So this gives us 6n squared minus 15n. What do they have in common? Well, they each have an n in common. You could also realize they each have a 3 in common. And so I'll keep in practice with taking out that common factor. That'll leave me with a 2n minus 5. 3 times 2 is 6. 3 times 5 is 15. That looks pretty good. And then I need a couple of equations. N equals 0. That one's pretty easy. 2n minus 5 equals 0. Might need a little bit more room. So I'm going to take that up over here. We'll add that 5 to each side. 2n equals 5. And last but not least, of course, divide by 2. We can take the lazy, maybe efficient way and just say it's 5/2. Or you could think, what is half of $5? That's 2.5. Either of those work. All right, let's take a look at 5. And again, 5 is a little bit weird because 5 has 3x plus 10x squared equals negative 12x. Again, this doesn't equal 0. So it seems like our first step should be the same, and it is. I'm going to add 12x to each side first. Didn't like how that plus came out. There we go. But when I do that, I need to add 12x to the other side. The question becomes, which term do I add the 12x to? Do I add it to both? Well, no, we just do it one time on each side. And so I want to add the 12x to its like term, which is the 3x. Okay, this will give me 15x plus 10x squared equals 0. There we go. This next step is completely optional. However, I always like to write mine in standard form first. So I'm going to put the 10x squared and then the positive 15x next. That's completely optional, but it's good practice to be putting your equations in standard form. Okay, factoring time. 5x is certainly common to both of those. 2x plus 3. 5 times 3 is 15. Yeah, that looks good. We get x equals 0. Remember, you can take the 5 with you, but you're just going to divide it off at the end. And 2x plus 3 equals 0. Good. And let's finish this off. Subtracting 3 from each side this time. 2x equals negative 3. And finish by dividing by 2. And that leaves us with x equals negative 3 halves, or half of $3 is 1.5. Looking pretty nice. 1 to go. Problem 6 brings up something that maybe you've asked on the last couple problems, where you might have said, how come you keep taking numbers from the right side and moving them to the left? And the answer is because that side had fewer terms. Right? For this side, I only had to get rid of one term and one term. Well, this side, if we want this equation to equal 0, I either need to get rid of both terms on the left or both terms on the right. And it doesn't matter which side you start with. You'll get the same answers by the end. For me, though, I'm going to look at this minus 1x squared, this negative 1x squared, and I'm probably going to get rid of that first. Just because I know if I get rid of a minus, it becomes a positive, and I slightly prefer working with positive numbers over negative, so I'm going to add the 1x squared to each side. Now, when I'm doing this, again, to be efficient, I'm going to try to do this all in one step. 3 plus 1 is 4x squared. So I'm also going to get rid of this 10x, and I'll do that by subtracting it. That leaves me with just the 0 on the left side this time, which is okay, as long as the equation equals 0. And on the right side, we end with negative 18x. From here, we want to see what each of these have in common. And I'm going to work this problem over here. So I get 0 equals. I think they each have a 2 in common, and they each have an x. That'll leave me with 2x. Let's see, half of 18 is 9. That looks pretty nice. From here, a couple equations. 2x equals 0, which is just x equals 0, or 2x minus 9 equals 0. Add your 9 to each side. Leaves us with 2x equals 9, and I need a little bit more room. Finishing this off, we divide by 2. And so again, you can leave your answer as the fraction 9 halves, or you can know that half of 9 is 4.5. Ta-da! So if your teacher wants you to do the bonus problems, feel free. They're fun ones. A bunch of them are review at those absolute values. Some of them tie into today's lesson, but I don't want this video to go any longer than it already has. So hopefully you guys feel comfortable using factoring, the zero product property in particular, factoring and the zero product property, to solve these equations. Now for today, we just looked at ax squared plus bx equations. Next class, we're going to bring back that c. So we have an equation with 3 terms, and we're going to talk about how it all ties together. So thank you for hanging out with me, and I'm excited to have you back next class for lesson 9.2.